Graphs provide us with an extremely useful way to structure and perform operations on data that are related or connected in some way. Consider a social network in which users have connections in the form of friends. So let's say we have a friend L for Larry here. And let's say that he's friends with Barry, and we'll give that the letter B here. And Larry is also friends with Harry, so we'll give that a H there. And then we'll have this line to show the friend connection there. And then let's say that Harry and Barry, they're also friends, so we can connect them two together like that. And then let's say Barry, he is friends with Sally. So I'll put Sally as a S here. And I'll have a connection there. And then let's say we have a new account and we'll call this person Clarence. So Clarence is over here. He's not friends with anyone. So he doesn't have a connection with anyone, but he's still sort of part of the social network. So what we can say is each of these circles, or each of these friends in this case, that's what's known as a node. And it's also can be called a vertex. So the sum of all of the nodes, they can be also called the vertices. Sorry, not the sum of all the nodes, but all of the nodes together are known as all of the nodes, or all of the vertices. So more than one node or more than one vertex can be known as the nodes or vertices. And then in between them, you have this line, and that's called a edge. So EDGE. And what we're saying is, in terms of graphs, we can say that a node has a edge between another node, and if that's true, then those two nodes are adjacent to one another. So we can see here, this section here, these are connected in some way because two of the nodes, or more than two of the nodes, they have some sort of edge between them. But here we can see that Clarence over here, he's disconnected. So I'll write DC here. So this is called an undirected graph because there's no direction between the two nodes in comparison to a directed graph. So let's consider we're traveling between countries via an airport. This is an example of a directed graph. Let's say we have an airport A and we have an airport B and we have an airport C. Airport A, it might fly to airport B, and airport A, it also might fly to airport C, and then airport B might fly to airport A, but airport C doesn't fly back to airport A, and airport C, it might fly to airport B, but B won't fly to C. So this can happen. For example, let's say we have a Los Angeles airport or something like that, and then it flies to, one of the planes there flies to a more remote location. Maybe it goes, I don't know where, to Laos or something like that. But there might not be flights going back to Los Angeles from Laos. There might be, but just as an example. So you might need to fly from Laos to Singapore, and then you can go Singapore back to LA. So these arrows indicate a direction. And with that, we can use that information to be able to traverse through connections. So the way we represent this, we can represent this in two different ways. We have the first way, which I'm going to do up here. And this will be known as an adjacency matrix. So I'm just going to put ADJ for adjacency, and then M for matrix. So the way this works is we consider each of these nodes. So we have A, B, C, and then we pair it with itself. So we have another A, B, C here. Let's just write this out here. So we got our matrix there. And the way we look at this is we say, well, is A connected? Well, firstly, the main diagonal here where the same node represents itself, there's no adjacency because the same node can't be adjacent to itself. It is itself. But then what we can look at here is we can say, well, A, is that adjacent to B? Well, A points towards B, so we give it a 1 there. And then A also points to C, so we give that a 1 there. Now if we look at the node B here, we can see that B does point towards A, so there's a 1 there. But B does not point towards C because C points towards B. So we have a 0 here. And then finally C points to B, but it doesn't point to A. So we have a 0 and a 1 here. And we can see that we've got four numbers 1, 1, 1, 1, 1. And that corresponds directly to these arrows here, or our edges. And then the number of columns and rows, because it's a square, is going to represent the vertices here. So we can easily find an element in this adjacency matrix if we have the index of the row and the column. So that means that the time complexity for a memory lookup, that's going to be O of 1. But as you can see, because we got this square here, for the number of elements, or sorry, the number of nodes that we have, or vertices, we're going to need to square that because we're going to need to have all of the pairs there, all of the combinations of the pairs between the two elements or nodes. So that's going to be O of n squared, but we know that n is going to be the number of vertices. So what we can say here is we can have O of v squared. So if we want a good time complexity and we don't carry out a space complexity, we might use an adjacency matrix. But let's say we do want to improve our space complexity. We might use something that's known as an adjacency list. So I'm just going to have ADJ L for adjacency list. So the way this works is we take each of our nodes, and that's going to be the first letter in each of the lists, or the first node in each of our lists. And essentially each of these lists are linked lists. So because we have a direction here, they relate to one another in a certain direction. So we can link them to one another. So A, we can see that that points towards B, but A, it also points towards C. So we can point towards that, and then we just finish off on the next pointer because we need to assign another memory slot. If you've seen the linked list video, each element in a linked list has its value and a pointer to the next value. So B doesn't point towards C, as you can see in this graph, but what the adjacency list, how it differs to the adjacency matrix is we consider all of the elements or all of the nodes that A is linked to. So we can see that A points towards B and A also points towards C. So B doesn't point towards C directly, but if we want to know the information which nodes does A link to, and we're referencing that or representing that in a linked list, we can just have A point to B, and then when we cycle through and we say, well, we can get the next element or the next node as C, that has contextual information to know that, okay, well, B and C, they're related to the list A because A is the start of the list, and then cycling through that shows everything that's A points towards. So in a similar way, we have B here, and B points towards A. And then we just have an empty pointer there because, again, C points to B, but B doesn't point towards C. And then we can say, well, C points towards B here. And then that's the only thing C is pointing towards. So one way we can represent this is in terms of memory, to be able to work out the time complexity, is if you've seen the linked list video, you'd know that if you have contiguous memory cells here, so this is memory, and then I'm just going to do something like this here. Maybe I have one more column here, and I have some rows here. Basically, the value A here in a linked list, each node is represented by the value and also the pointer to the next one. So what we would have here is A, and then we have this edge here, or this connection here, and that's going to point towards B. And then we're going to have another one where B points towards C, and that points towards nothing. And then we're going to have B, and then in this cell here we're going to have points towards A, which points towards something here. And then, you know, we're going to have C pointing towards B, and then there's like a pointer here. So I might have misaligned some of these squares here, but you get the general point that essentially the amount of space that we need is the number of the vertices plus the number of the edges. So we can say that and let's start with the space complexity for this one. The space complexity here is going to be O of V plus E. So in the same way that if you have two for loops next to each other, which O of n plus O of n is O of 2n, if we have the number of vertices, that simplifies to O of V, and then we can also count the edges of one another, and then they can simplify as well. So the space complexity is O of V plus E, and then the time complexity for this one here is going to be O of V. So we can see that, let me do that again, O of V, and we can see that this is worse because the time complexity is basically, you can see here that for each node we need to cycle through each of the elements in the list, and when we do that traversal, we know that linked list traversal is O of n, and here we've got the number of vertices, so that's O of V, and we can see that that's much worse than constant time, of course, but the space complexity is better. So in this example, it actually sort of looks like the space complexity is better in this one. That's only because it's 3. because we need 9 different slots here. So even though we have more than 9 slots here, or around that, presumably, you know, we're considering the case where we have large numbers here. So, or like large amounts of vertices. So things get better. And there's one thing to note is if you just ignore this line here for a second here, you see that oh, well, actually, hold on. Let's just do another graph here. So just real quick, if we have A and A points towards B, and then B points towards C, and then C points towards A, it's possible that you can just keep going around in circles. And this is what's known as a cyclic graph, as opposed to something where you can't keep on going around and around in circles, which is known as an acyclic graph. And it's just something to keep in mind, because some algorithm questions, you know, if you've noticed that you have a cyclic nature to it, you may want to do something where, you know, let's say you start an element A, you want to track some data associated with that node there, and then track some data with B, and then track some data with C, and then that way you know you've sort of traversed through all elements. Now in this case it looks pretty simple, but as your graphs and trees and all that become a little more bigger and more complicated, you know, you want to have some way out of it to determine if you've reached a certain node or not. So that's the video on graphs. I want to look into trees in the next video. So please subscribe to my YouTube channel, and I'll see you in the next video. Cheers.